Recording. Okay, Peter, over to you.
Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve? And what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who has kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. For the most effective results, Happy has advocated selecting your own engineers who are already familiar with your own processes and procedures and letting them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Happy began the series with an introduction to the elements of automation and the journey to your smart factory, and discussed the key issues: who, what, how long, when, and how much. Since then, he has discussed a series of skills, including total quality control, Six Sigma and statistical tools, problem solving, design of experiments, predictive analysis, benchmarking, product and process life cycles, engineering economics and road mapping. He has defined automation and automation methodology and examined the realities of the smart factory. Last week, he focused on sensors and chemical analysis. If you missed these earlier sessions, they have all been recorded and will be made available to you. In today's presentation, the 7th in the series, Happy explores 3 more of the essential skills: figure of merit, shared vision, metrics and dimensional analysis, and lean manufacturing. If you have any specific questions, please direct them to happy@iconnect007.com. So Happy, over to you.
Well, thank you very much, Pete. Let me bring my one up. So this is a very important set of topics today. I changed the order of them from the slides that we set out. I'm using just the same slides, but I thought I'd start with metrics and dimensional analysis before I delve into the figure of merit. These first 2 talk about variables and measures of performance, but they are measures of performance and independent variables that you may not have thought about. And I'll open up the concept that using these techniques, it's okay if you develop your own measure of performance or an independent variable, if it helps you correlate to the solution and answers that you get through different sets of data. So with that, we'll jump into this, which the first one is, like to say, is the metrics and dimensional analysis, which are chapters in the 24 essential skills. So although I'm only spending 20 minutes on them. The chapters are far larger, and the chapters refer to coursework and classes I've taken that be anything from 8 hours to 40 hours for the full understanding of it. Like I said, we talked last week about digitization and the smart factory and sensing, but there are intermediate steps, because what happens if you don't have the data and are not prepared to collect it? Well, all is not lost. You can still start, as I'll show you a couple of techniques that I've used in the last 50 years. And the first one is dimensional analysis, which will go into the methodology and the creation of dimensionless parameters in engineering. So I've kind of determined that there's 4 levels of metrics or measures of performance for both product design, process effectiveness, quality. And those 4 levels are no opinion. That is, you don't have anything. There's no attempt to inspect, improve. It's just kind of an over-the-wall process, no communication. Then there's opinion, and expert opinion is applied after or concurrently with design and manufacturing. Many times it's an inspection process by production engineers or CAM people in printed circuit fabrication, but it's still an opinion. Then there's an intermediate one called the figure of merit, which I've invented. So if both the process and the product are scored by linear equations developed by expert opinion and a consensus methodology that we'll talk about. And the last one is the metrics or measures that both the product and the process can be measured by physical data, which everybody can inspect and work with, and was supported in the first lecture about design of experiments, where we talk about qualitative and quantitative variables. But there's also 5 stages of these metrics, and that is kind of the age of anarchy that most people are still in. That's anything goes. We just run it by the seat of our pants. There's an age of folklore, about 25, where wisdom is actually passed from one generation to another over pizza and beer, informally, maybe documented or not. And then comes the age of methodology, and the way manufacturing or design for manufacturing is engineered is documented and is actually done that way, many times using the figures of merit. Then there's the age of metrics, which starts getting slimmer, where both the product and the process are measured in standardized ways. And then the actual age of engineering, where productivity is achieved through continuous quality improvement, much like it is in enlightened manufacturing. And so the first one is the dimensional analysis, which was created in 1877 by Lord Rayleigh. This was taught to me very early in my engineering career, and I'm not sure that if other chemical engineering universities taught this or not, but here it is. And the Rayleigh method is that you gather all the independent variables that are likely to influence the dependent variable that you're interested to try to develop an analysis or equation for. And if the R is a variable that depends upon the independent variables R1, R2, R3, etc., then the functional equation can be written as R is a function of these independent variables. Write the above equation in the form of CR1 superscript A, R2 superscript B, where C is the dimensionless constant and A, B, and C are arbitrary exponents. Then you express each of these quantities in the equation in some basic units in which the solution is required. And then by using dimensional homogeneity, you obtain a set of simultaneous equations involving the exponents A, B, C through M. You then solve these equations to obtain the values of these exponents, A, B, C, etc. And then you substitute the value of the exponents into the main equation and form the non-dimensional parameters by grouping the variables with exponents. So I'll give you an example of that. This is an example which is easiest, which is fluid flow in pipes. So gathering all the independent variables that are likely to influence the dependent variable, and that's fluid flow in pipes, either by head loss, energy loss, or some other value. So we have pipe diameter D, fluid velocity C coming in, fluid density rho, and fluid viscosity U. So if R is a variable that depends upon the independent variables 1, 2, 3, 4, then the functional equation can be written, Y is a function of dV rho mu, as seen here in the slide. So we write the equation in the form of C, variable 1, variable 2, to the exponent A, B, C, and D, where these are just arbitrary exponents. And they express each of the quantities in the equations as some basic units in which the solution is required. So pipe diameter, D will be in inches. It could be centimeters if you're doing fluid velocity, inches per second velocity, fluid density, pounds per square per inch, fluid viscosity, pound inch per second. And then using dimensional homogeneity, you obtain a set of simultaneous equations involving A, B, C, and D, shown here. And then you solve these equations to obtain the value of the exponents. And here, A will equal 1, B will equal 1, C will equal 1, and D will equal -1. When you substitute these exponents into the basic equation, and there's no overall constant C on this one, you end up with the equation D rho V divided by mu. Well, that is a thing that we call the Reynolds number. It was first described quantitatively in 1883 by Reynolds there in the UK. And Reynolds found that fluid velocity, fluid density, fluid viscosity, and pipe diameter determine the nature of fluid pipe flow. These 4 variables combined in a single dimensionless parameter that are called the Reynolds number. And it's called the Reynolds number because all the units cancel out. There is no units associated with the Reynolds number. It's just a number, a dimensionless number. And in many ways, I call this a pseudo-independent variable because what this is a stand-in for these 4 independent variables. But dealing with that many independent variables is very, very difficult. Whereas dealing with the Reynolds number, is a single pseudo-independent variable. And that allows us to create what we call the Moody diagram. You can see here where friction factors and relative pipe roughness can be plotted against the Reynolds number there along the bottom there, from 10 to the 3 to 10 to the 8. And with this, we can talk about turbulent flow, laminar flow, transition regions, smooth pipes, rough pipes, even material construction. And this is fundamental in mechanical engineering to flow in pipes, not just of liquids, but also of gases and other materials. But you can see that it would be extremely difficult to do this friction factor if we dealt with only one of these 4 independent variables that makes up the Reynolds number. But the Reynolds number itself solves this for us and is in fact based on physical data, but just not used individually. Interesting enough, there are 152 of these in the world of engineering. Engineering totally depends on these dimensionless parameters. I have them listed here alphabetically from acceleration, but it covers all the things in momentum transfer, mass transfer, heat transfer, and even fundamental electrical magnetism and electrical forces and fields for motors and things like that. You may have heard of some of these, Euler-Frank number, or ones like here. One that everybody's heard of is Mach number. Many people think of the Mach number as a velocity. Actually, it's a number. It has no units. It can't be velocity. It's actually the inertial force divided by the electric force is what makes up the Mach number. And when you exceed Mach 1.0, you've exceeded the speed of sound at that particular altitude because of the inertial and elastic forces. But there are other ones that I've learned to use a lot: Prandtl, Grashof, Nusselt, Stokes, Taylor, et cetera, through my career in the last 50 years. And in fact, these are essential. I don't know if you've ever seen all 152 of them. The one that we just talked about was the Reynolds number there in the middle of the chart. But these are really important. And without them, we'd have a much harder time, especially before the use of computers, of doing engineering design equations that run the world. So, this idea that we have created lots and lots of pseudo-independent variables in order to get engineering done led me to believe that it's possible for us to create other pseudo-independent variables if it serves a purpose. And what I developed and call a figure of merit process is one of creating, an equation and a measure of performance that we've not used before. And you look at that one, all you've got is opinions or too many variables, and you can't figure out kind of how to put together an experiment that deals with all of these variables that we might do, as we talked about in the first lecture on design of experiments and statistical analysis. So any kind of measure or metric is preferred over opinion, and it's better than no opinion. So a figure of merit is really a consensus-derived measure based on expert opinion. It provides a score that allows everyone to participate in improving the product or process. And one of the first that I created was a figure of merit that I call the PCB Complexity Index. And that is manufacturing printed circuit boards and looking to correlate different elements of quality and first pass yield with all of the independent variables that make up a printed circuit board. Wasn't able to achieve it. There were, 8 to 10 to 12 different significant independent variables that affected how you manufacture a printed circuit board. So we started working on creating what we call the complexity index, which is a figure of merit based on these significant independent variables. And how is that done? Well, the figure of merit process first starts with gathering experts that are associated with this product or process. And that is everybody, including purchasing or quality, manufacturing, engineering, design. And first, you define or identify this new measure or metric that's going to be developed. And second, you ensure that the relevance of the measure to communicate is why everyone agreed to be there. This typically takes a full day. Sometimes it's gone over to 2 days on really complex ones. sometimes you need to do some homework as surveying customers or needs to identify customers' measures to be communicated and identifying needs or expectations and collecting any data there. The fourth step is generating ideas, brainstorming factors and variables contribute to whatever this measure or performance is. Then you need to sort the ideas into groups, allowing time and not forcing people, but grouping these together. And then once you've got we call clouds of affinity groups, you define what that factor is about that group. Then you determine major contributors by multivariate paired ranking or some other method, normalize the scores and verify the data. And then you construct a weighted factor variables from 1 to 100. And this then creates your equation that's a score measured. So we'll go over these things, surveying customers or needs. Prepare before you start, kind of make a card of each response. We use the typical 3M Post-its of this on a wall somewhere. And this is kind of where we start with. Then we start brainstorming ideas by everybody in the group. We go around and each person brainstorms what they think is important in this without criticizing or anything like that. Whatever they say, we write down on a Post-it and put up on the wall. And we do this for a couple of hours. In other words, once you've gone around a couple of times and people say, well, I don't have any more ideas, you don't let them stop, but you focused on digging down deeper, into some level that you didn't wish to express, but now's the time to bring it out and put this idea down on a card that we've got up there. So you display all these completed ideas cards randomly laid out so that all the team members can see them. And then you start to arrange the cards in natural groupings. And again, this can take a couple of hours, but the purpose of this step is to collect the ideas that go with each other. And in silence, you're not allowed to debate. All team members should simultaneously begin to move the idea cards, collecting and arranging in columns the cards that each person believes belong together. And this process, again, can take a while because some people may arrange the cards and somebody else will come along and unarrange that particular pile and put it into another pile. So you've got to allow this completely take place. And then it's good to have a facilitator who's not involved in the process, but simply in facilitating, because you don't want to have arguments in which, one person believes that this card belongs in this pile and another person believes it belongs in this card. The facilitator steps in and asks the question, why do you believe in this card belongs in this pile? And they explain it. You say, well, how about if we reword, this idea this way? So that, and then you talk to the other person, why do you believe it's in this pile? And they explain, oh, well, let's reword this idea. So it clearly belongs in this other pile type thing. So again, this can take a couple of hours of interaction until everybody is settled with the groupings. So you're moving each idea into a category that are various ideas, but similar in terms of their what they're really primarily focused at and sorting these. And this typically kind of looks like this with the 3M Post-its in terms of the yellow being the brainstorming ideas, and then the blue being redefining some of the yellow ones. And then finally, if the cards are redundant, overlap them, but in such a way that they can still be read. And team members should freely change cards between groupings or create new groupings as they feel appropriate. It may find that if you move back and forth, that the ideas that you're moving needs to be in its own separate pile and not part of the pile that we've stocked there, because you get to the next step in returning back and forth the moves until the team settles on an arrangement that's some cards may be loners that do not seem to fit in any grouping. They should be left that way rather than try to force fit them into a grouping. And what you have now is these post-its that are in these natural groupings. Then you create a header card. And a header card is what the group believes that pile actually talks about. And in the simplify the, what may be all these different ideas, but what's fundamentally is this really talking about in only a few words? And these create the headers for these piles. And that's what we call it, a cloud of infinity, creating these header cards to make sure that each header placed at the top of a group captures the essential link among all the ideas beneath it and consists of enough words to clearly convey the meaning. And these are header cards that you have. And, drawing the finished clouds of affinity. In other words, the header cards now, describe all of the independently produced brainstorming ideas, into groups. And you review each group or category, and there's no right or wrong way. It could be a category that's, only one idea, like job design, or it could be a category like safety and ergometrics that has many, many brainstorming ideas behind it. But whatever they are, they represent what each team member feels is important about why they're there together and what they're trying to achieve. In other words, their particular gain of the senses, their contribution to the overall is supplied. Now you determine which one of these are major contributors. And you can do this about voting. You can give everybody a, number of elements divided by pi, number of votes to place, or ranking vectors, as you see here. I prefer the thing called the paired ranking. And the paired ranking, I think, is the most effective because you list all of your categories in both the vertical and horizontal axis. Draw a diagonal between them. And then we simply do a voting. In other words, idea category 1 versus category 2. How many feel that category 1 is more important than category 2? If it gets the most votes, it wins. Well, how about category 1 now versus category 3? And 3 wins, so it loses. How about category 1 versus category 4? Well, actually, it's a tie. Or category 1 versus category 5, it wins. Now we go down to category 2 versus category 3. Category 2 versus category 4, category 2 versus category 5, and so on. 3 versus 4, 3 versus 5, 4 versus 5. And then you count up the number of wins, losses, and ties. Well, this is the coefficient of a major contributor, my C sub n, 23201. Interesting enough, since category 4 had no wins it drops out. And in the one, the next step is that you create a weighted factor table about the categories. And you do it from one, which is easy for many years, all the way up to difficult to impossible, whatever that may. My example here is the minimum drill diameter and through-hole drilling from 1.27 millimeter. It's easy to do a 1, and doing a 1 mil diameter is difficult, if not impossible. Then you define the 50th percentile, 25th percentile, and 75th percentile as a weight. About 1985, Dieter Bergman and I undertook a look at a lot of PCB design variables and fabrication variables and created this coding of 1 to 100 from easy to complex. Be it this is 1985, but you can see different values there. So you create a linear equation by taking the number of votes, the C1, times its weighting factor, and the C2 and its weighting factor, and the C3 all the way. So you now have a scoring equation that everybody can agree with. And what it comes down to, in my opinion, is that we've taken opinion, and through this process, we've kind of cubed the opinion and now turned it into pseudo data. But it's surprisingly accurate, I've found. Once you have this scoring, in this particular case, we were focusing on producibility. We now had a measure of producibility at the design stage. And we could go back and correlate yield and ease of manufacturing and cost with this scoring equation that provided design with the ability to know whether or not it had designed something that's producible. And we have also agreed that if a score of 45 was a minimum that we accepted, then design, if they were at 55 or 65, it wasn't ready to be turned over to production because it hadn't reached 45 yet. And they go back and improve and change some of the design until they get at least the score of 45, which everyone considers acceptable. So that's in many ways how we came up with the complexity index of how complicated is the printed circuit board, both from fabrication, assembly, and design. I use what we call the Gompertz curve, which Benjamin Gompertz in 1825 created this mathematical model for time series. I show you right there. And it asymptotes from 0 to the asymptote. But I use
Have we lost you, Happy? We're just waiting for Happy to sign back on again. Okay, we've lost Happy, but we'll wait a few minutes and just see whether he can sign back in again. Hello, Happy. We lost you for a few minutes there.
Yeah, I've lost my interconnect connection, so I'm back in there.
No problem.
You know, I don't quite know when I lost it as I was chatting, and then, but I'll let me find out where I was. Yeah, can you see that?
Yeah, I'm just trying to make you the whole co-host again.
Say again?
I'm just trying to make you co-host again.
Oh, okay. Oh,
I don't seem to be able to find you.
well, let me see. Oh, I got to do the share screen. How's that? Oh, you need to, I'm disabled.
Okay, you
It
should
says-
now be
It says Happy
co-host.
Holden is co-host now
Can you make me the
on my screen.
share screen, Bill?
Yeah, I've just done it, Happy, so you should be able to share your screen. Yeah, you're co-host now, Happy, so you should be able to share. Hello, Happy, you still there?
I think we've lost him, Bill.
Yeah, he's gone again. I did make him co-host, but he's disappeared off the screen again.
Yeah, no, it did show on my screen that he was co-host, but I can't see him on the screen at all now.
We'll wait a few moments, and if we can't do it, we'll have to find another way of making up for this last 25 minutes. We've not actually had this before, have we?
No. Because Happy had always said if he did lose his connection, then he had pre-recorded it anyway.
Yes.
But do you have the pre-recording?
I don't personally have the pre-recording,
No.
but I mean, Happy will have pre-recorded this, so
Yeah.
nobody will lose anything at the end. It's just a bit unfortunate he can't talk his way through it,
Exactly.
but he's definitely not here at the moment.
No.
I'm going to switch off the recording for a bit.
Okay.
changed my mind. Pause.
Okay, you're seeing that and hearing me?
We can hear you, but not, we haven't got your screen yet.
Oh. When you have the screen.
We just have your name showing in the center of the screen, Happy,
Huh.
but not your presentation. Right.
See anything?
Yes.
Oh,
Yeah.
good. Okay.
We haven't got a full picture. We've got a very surprised looking little animal now.
Yeah.
How's that?
Yeah.
You got it?
It's
Okay, so I think this is when I dropped out, was talking about this Gilbert's curve that correlated to first pass yield based on the complexity of the multi-layers being tested. The data analysis showed that this curve was in plus or minus 3%. This is very useful because one of our best customers had designed a new computer using a single multi-layer instead of multiple multi-layers with a backplane. But it was the most complex multi-layer we'd ever seen. And our first pass yield predicted it would only have an 8% yield.
We've just got your home screen, Happy.
We got my, what screen?
The home screen with your cat or a cat.
I'm not
Some
sure.
Some sort of
What?
cat.
I
or a
don't
lynx.
know anything about that. Cat?
Yeah.
Oh, I see. You got that screen. Oh, yeah, that's yeah, okay. Well, let me see.
You need to reshare again.
How do I
So unshare and go back and share again and pick the window.
stop. Okay, go back.
Stop sharing, yes.
Yeah, do my sharing again.
Came back the same again.
Oh, there we go. How's that?
Got it.
Yes.
Yes,
Wonderful.
thank you.
Thanks.
Excellent.
Okay. This is where I think we dropped out. But,
Yeah.
Anyway, like I said, one of the examples of how this paid off was that when our customer produced this single multi that was complex we ever received, this model predicted we'd only have an 8% yield, which management said, no way. We always get above 80% yield. But we convinced our management, no, this model is pretty accurate. And we've informed the customer that we're only going to get an 8% yield, but they're willing to pay the price. It's just that we're going to have to start a lot more blanks in order to meet shipment date. And even though management objected, said that got to be 80%, our actual yield on this production was 12%. So we met delivery and profit margin. And working with the manufacturing process and improving the design, we moved up to 50% yield as they simplified the design, and ultimately up to an 84% yield. You can see there. So, although we always like to get 90 or 95% yield, you can design a printed circuit board that's almost impossible to build, which is what a customer did. Like I said, our model indicated we'd get only 8% yield, but they said, we'll buy it. You know, we must have the boards and we'll pay any price. So we said, great. So with that, in the last few minutes, talk about basic elements of lean manufacturing, which focuses a lot on zero defect manufacturing and demand pull production, designing flow processes to level schedules, managing design data and computer-aided tooling, as well as optimized product design and design for manufacturing. Build upon what we've talked about already: design of experiments, statistical process control, and total quality control. The fundamentals of TQM was that react to uncertainty by adding complexity. And a fundamental principle of lean is anything that does not add value to the product is a waste and must be reduced or eliminated. So we react to uncertainty by adding complexity. If we don't trust the vendor's performance, we add another vendor. If we don't trust our capacity, we add lead time. If we don't trust our inventory levels, we add more inventory. If we don't trust our quality, we add rework station. If we don't have time to do something right, we add more time to do it over. In other words, our business culture reacts to uncertainty by adding complexity. Gaining control over and reducing complexity are the primary objectives of total quality management. Lean has the task of organizing and simplifying complexity in manufacturing. Lean in TQM is a simpler process that has less inventory, less floor space, less people, less process steps, less part numbers, less options, accessory manuals, paperwork, and less chance for error per unit of output. And so Lean and Six Sigma go together in terms of, you know, Lean eliminates variability, and Six Sigma identifies and eliminates complex sources of variability. So we talked about Lean and Six Sigma, but they contribute to this idea. You know, Lean elements are many: value stream management, the 5X visual factors, standardized work, Kanban line control, streamlines, and continuous improvement. So integrating Lean into the Six Sigma program is an important, using Lean tools to accelerate the improvement and change to manufacturing, especially eliminating waste. And waste can be waiting. How much lag time is there between production steps? We showed in the Whelan video that from drilling to final fabrication, the entire metallization, imaging, plating, etching, stripping, solder mask, and final finish takes only 258 minutes. So if your manufacturing time between those things involve days or weeks, anything above 258 minutes for the final finish of the board is wasted time. And that wasted time is where you end up with oxidation, scratches, bumps, things, fingerprints, everything else. And so eliminating that as waste can be a major focus of automation in terms of defects, workforce, motions, to design a simpler manufacturing system. If you go back and actually look at the articles written about the Whelan facility, you'll find that they make a multi-layer in 60% fewer steps than you do. And the reason is that they've taken out all the wasted steps due to time and sitting around, in the shop. And that's one reason why no matter what the volume, from 1 panel to 100,000 panels, the manufacturing time is still the same. less than 2 days. And products are shipped, once they've sent it to the shop within 2 days, no matter what the volume and no matter what the process. They go from 1/10 of an ounce to 4-ounce coppers, intermixed, 5 different final finishes, multiple different types of materials, still the same lead time because of the simplification of the manufacturing. So just in time is one of those, although just in time with what we've dealt with the supply chain, is looking back at just in case inventory levels. So as you rebalance your supply chain and, what can return in reducing inventories, rather than having, building inventory for the just in case by emptying the swamp. And this can be a major, again, focus of automation and future business activities. And utilizing CAM and CAD systems does not indicate that you can design a high quality board. As I've illustrated here, humorously with an Escher diagram, a computer doesn't know that something is not manufacturable. If you look at this rectangular extrusion bracket using the ambiguous hex nuts, techniques like that, it's an optical illusion, but nonetheless produced by a computer. Many times it doesn't know that this cannot be built. And many times that's what we have in the output of the EDA tool from a PCB design. You can design something that cannot be built or not be built at profitable or yield levels. And the same is true for assembly. This happens to be from a famous article by IBM on the IBM design for assembly methodology, where have these factors in their assembly process and the scoring in terms of number of points. This allows their designers to look at, how do I get a discount? Well, you need 61 to 75 points to get a 10% discount, 76 to 100 points to get a 30%. But if your board is 0 to 60, then you're going to pay a price premium of 10% over or 30% over. And these relative prices, are a business negotiation. But implementing this design point from a report card ended up that everybody in IBM was shooting for the above 60 points measure of performance in order to get some kind of discount rather than making it harder and harder to manufacture. In fact, designs were easier and easier to manufacture. And another way that we're trying to do that is through IPC's 2581 DPMX, which will flow directly into the IPC CFX program that we've talked about. And theory of constraint is another methodology identifying limiting factors in terms of that, as well as the Toyota way, the Kanban method, and the Kanban Hijinka box, based on 5 relative items describing workplace practices conducive to visual control and lean production. Also, what we've talked about is simplifying the work centers through automation and material handling, as well as selecting advanced manufacturing equipment that may be flexible in terms of flexible manufacturing systems for the smart factory of the future. So the 24 Essential Skills ebook has a complete chapter on DFMA. We can study at your leisure, and we're not going to cover that in this series. And the figure of merit may wear thin uses the critical factors as variables in design of experiments to produce an equation based on data rather than opinion. If there's more than 8 to 10 variables, both qualitative and quantitative, then a Toguchi orthogonal array will have to be used, which is an advanced statistical technique that you can study on the Engineering Statistics Handbook we talked about in the first one. So with that, I apologize for losing my internet, but thank you for your time, and I'll see you next week. And like I said, if this is all information you've never seen before, like I said, read through the books that we provided. And then if you still have questions, send them to me, because you won't, you won't find the figure of merit or too much about dimensional analysis on the internet. It's a relatively, well, the figure of merit is something that I invented, and dimensional analysis is a fairly obscure but important part of engineering today. With that, thank you for your patience and your time, and hope next week I don't have an internet problem. Like I said, you can never tell. Thank you very much.
Thank you, Happy.